students, welcome to another iCampSA video. Today we'll be doing calculus and specifically focusing on the graphical interpretation of the derivative, which is used to determine whether a function is increasing or decreasing. But before we get there, let's start with this question 8. It's from 2025. It's basically touches on what we've already covered, which is the first principles and also the derivatives, before we get into the graphical interpretation of the derivative. Okay, so for 8.1 we're asked to determine f prime x from first principles, and if you remember, the equation that we use to determine the derivative from first principle is f prime x is equal to lim as h approaches 0 of f at x plus h minus f at x over or divided by h. Okay, so we already have f at x there. F at x, we know that it is f at x is minus 2x plus 3. Let's determine f at x plus h. F at x plus h, I'll just write it here. F at x plus h is equal to minus 2 into x plus h. Wherever we see x, we substitute x plus h plus 3. And this is equal to minus 2x minus 2h plus 3. Then we can go ahead and substitute this in the formula. F prime x is equal to lim as h approaches 0. What is f at x plus h? F at x plus h is minus 2x minus 2h plus 3 minus, what is f at x? F at x is minus 2x plus 3 all over h. Let's add or subtract the like terms. Lim, we haven't yet substituted the h, so we still have to keep this sign of lim as h approaches 0. Okay, so as we can see from there, that minus 2x plus 2x will be 0. This and this would cancel, and then 3 minus 3 also that will cancel. Therefore we'll be left with minus 2h divided by h minus h divided by h. So the h would cancel the h, therefore the h would cancel the h. Okay, therefore what happens here, I think I've done that correctly. Okay, therefore what happens, lim as h approaches 0, we're gonna have negative 2, which happens to be a constant, so we can't substitute 0 or is 0 for h. So therefore f prime x will be just negative 2. F prime x will be negative 2, and that is your answer. Okay, then from there let's go to question 8.2.1. so we're asked to find the derivative of g of x, which is g prime x. So it hasn't been specified that we need to determine it from the first principle, so we can use the power rule in order to determine this. So g at x is equal to, this is 8.2.1, g at x is equal to minus 3x to the power of 4. G at x is equal to minus 3x to the power of 4 plus 2x plus 2x. Okay, so the derivative, which is g prime x, will be, remember, according to the power rule, we take the exponent to multiply the coefficient. Therefore we're going to have negative 12x, and then we subtract 1 from the exponent, therefore we're going to have 3. And then for the other sum, since we have the variable and just the variable with no exponent, which would become 1 essentially, but we know that the exponent is 1, so we take 1, multiply the 2, and then we subtract 1, of which will leave us with x to the power of 0, and then x to the power of 0 is 1. Therefore here we will be left with 2. And that is our answer for this question. Okay, and then next we are asked to derive y with respect to x. Okay, for that, what is that? Yes, for that expression that we have there. And remember, when we have fractions, we first need to deal with them first, then or rearrange them, if I may say, or simplify them before we can derive. Okay, so first thing first, y is equal to 2x to the power of 4 plus 1 over x squared. So for 8.2.2, y is equal to 2x to the power of 4 plus 1 divided by x to the power of 2. X to the power of 2. Yes, I got that correct. Okay, so I said the first thing, we need to rearrange the fraction, and then in order to rearrange using the laws of exponents, we know that we can change the power, or yes, the exponent of the denominator to -2 in order to just have a linear expression. But another way, we know that since that x squared is a common, what you call this thing, is a common denominator, we can split the two. We'll have 2 times x to the power of 4 over x to the power of 2 plus 1 over x to the power of 2, and therefore y is equal to 2 times x to the power of 4 over x squared will be 2x squared, and then let's rearrange 1 over x squared. We're gonna have 1 plus x to the power of -2, and then once we're here, we can now derive this expression. Therefore, the derivative of this expression, or yes, dy dx, will be equal to, we're using the power rule, 2 times 2 will be 4x, yes, and then 2 minus 1 will be 1, plus, or it's actually going to be minus 2. We take the exponent to multiply the expression, so we're going to have -2x to the power of -3, and there you have that, Okay, so yeah, that's how we'll approach doing these questions. Yeah, now that we are done with them, we can go to graphical interpretation of the derivative. Let me see where we left. So last time we left on finding the point of contact where the tangent touches the curve, but the basic understanding or basic introduction of the introduction was done, so we're already familiar with that. So right now we just wanna determine, or just wanna explain what this means graphically, what the derivative means graphically. Okay, so we said we can use the derivative to determine whether the function is increasing or decreasing at a point. So whether we have a negative or a positive derivative, that can tell us whether the function is increasing or decreasing at a specific point. And remember that a derivative gives us the gradient of the tangent, so when we have let's say a function like this, let me also draw the Cartesian, let's say, and then at some point here we have the tangent to the function, that line that you see there, we have a tangent to the function. Okay, so, and since we know that the derivative gives us the gradient of the function, so we can use to determine whether the function is increasing or decreasing. For example, with just that, what we have right now, is when this situation will occur when the derivative is greater than 0, so in other words, for number 1, this is actually number 1, if f prime x, the derivative is greater than 0, which means it is positive, then the function is increasing. Then I'll just use f for the function, or maybe for this one, let me just write the function is increasing. function is increasing at x is equal to a. At that point, let's say this is our a at that point. Okay, let's show another scenario where our function will also be increasing. What do I need? Okay, copy. So that's the first thing you should note. If the derivative is positive, greater than 0, then the function is increasing. And then we can also have the following. Let's say we have the function of this nature. It could even be a parabola. It's a little bit ugly, but you get the point. Yeah, let's see. Yeah, there we have it. Yes, it could be a parabola. And then at that point A, if at that point A, we can also see graphically that our function is increasing. So therefore our derivative will be increasing again. Do I have to write it? Yes, it's still greater than 0, so our function is increasing. In fact, let me just copy this statement to here, to right there, and then I'll just drop this one to here. And there you have it. So it's the same thing here. The derivative is greater than 0. Let me use f prime x is greater than 0 at x is equal to a. And then let's go to number 3. Now if the derivative is equal to, let's start with less than. If f prime x, the derivative is less than 0, then you can already know that will mean that the function is increasing. Then f, the function, is decreasing. My bad if I said increasing. It's decreasing at x is equal to a. At that point of contact. Okay, let's quickly draw a sketch of what we mean by this. I'll just take the one copy for the parabola here. Let's paste it there. And then what we're gonna do now, because we are dealing with decreasing, let's move it to this side. Yes, that is our tangent there, and it meets at a, and then our function will be decreasing if the derivative is less than 0 or is negative. Okay, and then once again, let's also paste to maybe another example for maybe an exponential function. Still, if we have this nature, our function is decreasing at a. So once again, f is decreasing at x is equal to a. Okay, and there you have it. And then for this was number 4, let's name this now number 5. Yes, now let's say our derivative is equal to 0. Let's say we're deriving a constant of which would give us 0. Then that what happens is that the function is not decreasing or increasing. It's not decreasing or increasing. Therefore we say we have a stationary point. So if f at a, or the derivative at a is equal to 0, then f has a stationary point. has a stationary point at x is equal to a. At x is equal to a. Now let's show this graphically what we mean. Okay, let's say our function, so a stationary point can also be our turning point, and it can also be what's it called this thing, a point of inflation if we are dealing with what is this, cubic functions. Yes, if we are dealing with cubic functions. And then so we say f at a is equal to 0, then the function has a stationary point at x is equal to a. Okay, at x is equal to a. Okay, and then we also have another scenario. This was number 5. Another scenario is this. Let's say for number 6, if we have the following, let's say our function, especially when we're dealing with the parabola, is increasing before the stationary point and then decreases. As you can see with this function that we have here, it's increasing in this side and then we reach a stationary point and start decreasing. We say this function is both increasing and decreasing after the stationary point, so we say the function is both increasing and decreasing. We can also have another situation whereby the function is decreasing and then increasing, especially when we're dealing with the parabola. So we're saying the function is both increasing and decreasing. If we were to just define is just the nature of the function, at that point, So what I'm saying is, if the function is increasing before the stationary point and after the and decreasing after the stationary point. We say, or vice versa, maybe in brackets, or vice versa, we say the function is both increasing and decreasing. It's both increasing and decreasing. Okay, so let's quickly sketch this function I'm referring to. Let's say we have a parabola like that one, and then we'll have to turn that one around. So what is happening here, the function has a stationary point there. Okay, and then let's do another one here. Let's do another one. And that is your A, that's your stationary point. Okay, that's a stationary point there. Okay, so we will say the function is increasing and decreasing at x is equal to a. At the stationary point, it is both increasing and decreasing. Okay, saying f is increasing, in fact for both increasing and decreasing. So with this one, it doesn't matter whether we start with decreasing or increasing, you know, because it's basically doing the same thing at the same time. So we say function is increasing and decreasing at x is equal to a. At x is equal to a. Yes. Okay, so that is that. And then let's go to cubic functions. Just a little bit of interpretation of cubic functions. Let's say we have, okay, this would be number 7, and how we'll interpret the cubic function. So what happens also in the cubic function, you also have a stationary point, you know, but here there was something a little bit different here, because a cubic function will not well, let me see, it can increase then decrease because we have many cubic functions, but for sake of simplicity we'll just deal with the simple cubic functions here, the one that increases maybe before the stationary point and then increases again after the stationary point. So yeah, okay, maybe let me sketch this before we even get to, let's say you have this cubic function that is your stationary point there. That's a stationary point here. So as you can see that the function before the stationary point is what? Is increasing. Increasing, and after the stationary point it is also increasing. So we say this function is what? It's just increasing. So we say f is increasing at what? At a. Is increasing. F, why am I writing it this? F is increasing at x is equal to a. And then the other situation will be when we have a function that decreases, you know. Let's say our function go like this, and then like this, yeah, and then we reach our stationary point there. So the function is decreasing before the stationary point and also decreasing after the stationary point. Decreasing. Therefore, we say this function is decreasing. F is decreasing at x is equal to a. At x is equal to a. Okay. Okay. Yes, we have. Let's see. Let's quickly do an example. Not even sure, just call it example 1 for today. Example 1. Let's quickly do an example. Let's say you have the following. Let's say you have this function, a function of this nature. It's a cubic function. Yeah, it's not drawn to scale. Say you have that function. These are your y and x values. Okay, so you are given, it's a cubic function, of course, obviously, given f at x. I think this will be a good segue to our next topic, where we'll be covering cubic functions. I think cubic functions are much more easy to understand once you have done calculus, or much more easier to interpret. So we're given the following, and then the question asks us to determine or find whether, and this is function f, by the way, whether f is increasing or decreasing just say number, or decreasing at the following point. So for A, at x is equal to -2, for B at x is equal to 0, at C at x is equal to -1, and then for D at x is equal to 3, and then at E at x is equal to +2. So we already know that's whether, when we want to determine whether a function is increasing or decreasing, what do we use? We use a derivative, the first derivative. So first thing first, we need to find the first derivative of that of that function. So we have f at x is equal to 2x cubed minus 3x squared minus 12x. Let's find the first derivative for this function. F prime x will be 6x squared minus 3 times 2 is 6 again, just x now, minus 12. That's the first derivative of this function. And then once we are here, basically what do? We have to go ahead and substitute this. Let me bring my calculator. We have to go ahead and just substitute the x values here, and then see if the derivative at those points is negative or positive. Okay, I can't seem to find my calculator. Okay, let's just do it. So for A, we have to substitute what? X is equal to -2. So f prime at -2 is equal to 6 times -2 squared minus 6 times -2 minus 12. This will be equal to, we have 2 squared is 4, 4 times 6. 4 times 6 will be 28, will be 24, sorry, will be 24, I believe. And then -6 times -6 will be times -2, sorry, will be +12. +12 minus 12. Okay, the last two terms will cancel, so we're just gonna have 24. Therefore, since 24 is positive, therefore f at -2 is greater than 0. Therefore, since f at -2 is greater than 0, therefore the function is increasing. Therefore, f is increasing. And then B f prime x at what? At 0. At 0 is equal to 6 times 0 squared minus 6 times 0 minus 12. This will be minus 12. This will be minus 12. Therefore, f prime at 0 will be less than 0, of which it means therefore the function is decreasing. Therefore, f is decreasing. and then the next fx value is -1. So for C, f prime -1 is equal to 6 times -1 squared minus 6 times -1 minus 12 minus 12. This will be equal to -1 squared is 1, 6, 6 plus 6 is 12. This would be 0 actually, 0. Therefore, this is a stationary point. This is a stationary point. So we say the function is both increasing and decreasing. So we say f prime is equal to 0. Therefore, f is both increasing and decreasing. And there you have it. So that's how you will do that. Please do the last two questions, and then because I want to cut this video now. I don't want to make this video too long, and then our next video we will be doing more examples, and also the second derivative which determines concavity for our functions, and then we'll dive into cubic functions. And then yes, thank you for attending this video. I wish you good studying and good luck.